Welcome to Module 4. This is the first recording for the lecture for this module, and we will talk about probability. All right, the objectives of this module are that by the end of it, you should be able to explain the concepts of a probability experiment or related to a probability experiment, interpret a probability, list its properties, and explain how to calculate. Explain what a complement of an event, joint events, and union events are. Explain what a contingency table is and calculate the associated probabilities. Calculate the probability of a complement of an event. I have this all by itself because this is a very important concept that will be very helpful later on. Differentiate between independent events and mutually exclusive events. Those are very important concepts that will be helpful in subsequent chapters. Explain what a conditional probability is and how to calculate it. And calculate probabilities using the multiplication rule and the addition rule. And finally, should be able to use the accounting techniques to calculate the number of outcomes of an experiment. So these are our objectives for this module. All right, one thing I did with this module, I organized it slightly differently from how it's organized in the book. I hope that the way I structured the module on the slides is a little more straightforward. At least that's what I think. But to avoid confusion, every section that I cover, I will write the section or subsection that it corresponds to the textbook. Like this section is in order, and this corresponds to section 4.1 in the textbook. All right, let's talk about experiments, outcomes, and sample space. All right, an experiment is just a process that when you perform it, it results in one and only one of many possible observations or outcomes. And an outcome is just an observation that results from performing an experiment. The sample space is a collection of all possible outcomes of an experiment. An event is just a subset of the sample space with one or more outcomes. Now, if the event has only one outcome, we call it a simple event. Sometimes people call it a sample point or an element, and we'll designate it by this E sub I. If it has more than one outcome, we will call it a compound event. And that's the difference between the simple event and the compound event. All right, here's an example to see how this works. All right, so here we're playing a game with a 12-sided die. So in this case, the question is, well, describe the experiment. Well, the experiment is very simple. You simply consist of rolling the die. That's the experiment. What is the sample space? Well, if you roll this die, you could get, as you can see from the picture on the slide, numbers between 1 and 12. So the sample space contains all the numbers from 1 to 12. Now, what would it be a possible outcome? Well, it could be any number that results from rolling the die. So any number between 1 and 12. What would it be a simple event? Well, any number from the sample space or any outcome that results from rolling the die. For example, here is the event of obtaining a 7. What would it be a compound event? Well, any event that contains more than one outcome. For example, here's an event with 1, 2, 3, 4, 5, 6, 7 outcomes that corresponds to the event, an outcome that is an odd number. So I hope this example helps you see how we apply the different definitions. Here's another example, perhaps a little less straightforward. But in this case, 3 to 4 year old children are weighed. So what is the experiment here? Well, the experiment is weighing a child, right? What would it be a possible outcome? Well, any number, any weight that you obtain, let's say 13.5 kilograms. What is the sample space here? Well, here I pulled the answer right away because it's an infinite number of weight values. This scale maybe rounds up to half a kilogram, but you could have another scale that gives you maybe thousands of a kilogram. But you can see each child will have a slightly different weight, so you get many possible numbers of weight values. So the sample space, I claim, is an infinite number of weight values. What would be a simple event in this case? Well, it would be the weight that you obtain from weighing one child, let's say 19.5 kilograms. An example of a compound event, maybe all the weights are above 20 kilograms. So I think you agree with me that this contains many weights, because many children will be heavier than 20 kilograms. Again, I hope that these two examples help you to illustrate these definitions. All right, so now let's go on to section 4.2. I'm still following the order in the textbook. And here we want to talk about probability, its properties, and how it's calculated. All right, probability is just a numerical measure that indicates how likely an outcome is when you perform an experiment. And we're going to designate it with a capital letter P. So when you see this P like that, that means probability, and the parenthesis encloses the event, that name we give to that event. In this case, I'm using E sub I, which is what we say we'll use to designate a simple event. So P of E sub I means the probability of one of the simple events, or one of the outcomes of an experiment. Or we can use P of A, so that will be the probability of some event A. Now, how do we interpret this probability? Well, probably from listening to weather forecasts, you know that when they tell you, the probability of raining is 0%, that means impossible for any rain. Or sometimes they give you a probability of 100%, or the probability of 1, meaning that for sure it will rain. And sometimes they're not so sure, and they say, well, there is a 50% chance, so that, like indicating that it may or it may not rain. Sometimes they give you probabilities of, let's say, 0.3. Well, then you know that it is more unlikely that it rains, but it could rain. Or if they give you a probability of rain of 70% or 0.7, then you know that it is more likely that it will rain. All right, but this is how you interpret this probability, and I think you are all familiar with this. So in terms of the properties of probability, I think you are familiar with the first property, which is the probability of any event, simple or compound, is always between 0 and 1. Always. You cannot have negative probabilities, or you cannot have probabilities bigger than 1. Such numbers are not measures of probability. Another very important property of probability is that the probability of every single event, or of every outcome, if you sum the probabilities of every outcome of an experiment, they must add to 1. If this is not the case, then your assignment of probability, even though maybe between 0 and 1, is not correct, because the total probability is always 1. And we will use these properties later on when we talk about probability distribution. So very important, please remember that. All right, so now that we talk about probabilities, the next question is, well, how do we assign a probability to an event? Well, there are two approaches. One is called the classical probability approach, or method, and that's for the case when the outcomes of an experiment have an equal chance of occurring. Another method is where we use the relative frequency. Remember in chapter 2 we talk about frequency distributions, and we learned to compute the relative frequency there. So we could use these relative frequencies as probabilities when the outcomes of an experiment do not have an equal chance of occurring, but when we can repeat the experiment. And finally, we have the subjective probability. This is when the experiment does not have outcomes with an equal chance of occurring, and we cannot repeat the experiment. So in this case, we will assign what is called a subjective probability. All right, let's talk about the classical or theoretical probability. So remember, in this method is applicable if every outcome of the experiment has an equal chance of occurring. And because of each outcome has an equal chance of occurring, we're going to spread the total probability of 1 among all the outcomes of the experiment so that we can comply with this rule, the rule of the total probability being 1. All right, with that in mind, then it makes sense that the probability of a single outcome is 1 over the number of outcomes in the sample space. Now, if you have a compound event, when you have multiple outcomes, then the probability of that event will be the number of outcomes in that event divided by the number of outcomes in the sample space. All right, let's look at some examples of this. Let's retake the example of rolling a 12-sided die. And here we are going to assume that this is what is called a fair die, means is not adjusted or modified so that it will favor certain numbers, and we will roll it in such a way that it rolls randomly so that not a particular outcome is favored. So if we have those conditions, then every outcome from rolling the die has an equal chance. So the probability of rolling a 7, of course, is 1 out of the 12, because there are 12 elements in the sample space, and that probability is 0.0833. Now, the probability of rolling a number less than 3 is now, if you look at the sample space, less than 3, you have an outcome of 1 and an outcome of 2. That's the only 2 outcomes. So now you have 2 outcomes in this event out of 12. So this corresponds to a probability of 0.167. Here's another example. In some inspection step of a process, a technician, due to an incorrect instruction, he misclassified bad parts as good parts. And the technician knows that he misclassified 7 items or 7 parts. Now, there is a box where all what we think are the good parts were placed, and it contains 63 parts, and the 7 bad parts are in there. And all parts are in the box are equal. In other words, the defective parts can we not distinguish it from a good part unless we do some detailed inspection. So if the technician draws 1 part at random from the box, the question is, what is the probability that that part is a bad part? So again, when he puts his hand in the box, he doesn't know if he's touching a bad part or a good part. So he has no way of distinguishing it, and he's drawing a part at random. So in that case, every part in the box has an equal chance of being selected. And therefore, we can say that the probability of drawing a bad part is 7 out of 63, or 0.111. All right, I hope these 2 examples illustrate when it's possible to apply the classical probability approach to calculate a probability. I'm going to stop here. In the next section, we'll talk about the other methods to calculate probability.